Mic testing. Hello, hello, hello everyone. Welcome to the live stream. And today we are going to do something different, not working on crochet engine. This is part of our Let's Make series, and today we are going to code something known as Julia set. I came across let's see the what is Julia set exactly. So this pattern that you see, the amazing pattern, uh, it's asking me to, yeah, it's, yeah, this thing that you see right here, it's known as Julia set, and it's a really interesting pattern to look at. And I was thinking that if I could make it, that would be really great. Tushar Khan says, big fan, bro. I am your big fan too, brother. So, yeah, this is what is known as Julia set, and I just know that this pattern is called Julia set. I don't have much idea about what it is exactly. So I'll be trying to understand what it is live on the stream, and after we have sufficient knowledge of it, then I'll try to implement it in OpenGL and C++. Hopefully we can complete it in today's stream. So without wasting any time, let's get right into it. So I am using the classic Wikipedia text here. Julia set in complex dynamics. The Julia set and the set are two complementary sets. Okay, so it is some kind of a set in complex plane, and I can see that it has some formula which is function of z, a complex number, is equal to z square plus c, which is some constant in complex plane. Okay. So this function consists of values with property that all nearby values behave similarly, and it has to do some repeated iterations of the function. Okay, so we have to work with this formula here, and maybe we can skip the formal definition. It's getting too much into the mathematics, and I don't think we require that much to successfully pull off a simulation. So I think we can start with uh, coding the simulation, and we can refer back to this Wikipedia page as we feel the need to do so. And yeah, I have two options right now. Like, I can use my crochet engine framework for making the simulation, but this then the stream would be really short because we we would have everything ready, and I don't want to do that. So I would create a simple framework or a OpenGL wrapper just to create this simulation. And as I can see that this Julia set, it's some kind of a boundary, and it it is going in a circular fashion, and maybe we can think that uh, out of this region, out of this pattern, the function it diverges, and so that's why we don't see the patterns outside. And yeah, we are going to do that. If like, we have two possible ways in which we can implement this in OpenGL. Maybe we can uh, use primitives like triangles and some geometry to construct this, but that would be too much of overhead, because like if you can see, like there is too much of geometry going on here, and if we try to implement it using a triangle, then that would not be an optimal solution for this. So maybe what I'm thinking is we can use the fragment shader, and we can actually you know iterate pixel by pixel, and iterating pixel by pixel, we'll just have to check whether um, that pixel currently converges or lies inside this region. Then we give it a specific color, and otherwise we give it a different color. Hi Vishal. So yeah, that's the plan for now. Let's get coding. So to-do list, understand Julia set. I think we have pretty much done that, and let's get to the coding part right away. So I'm not going to use any pre-made wrappers of my game engine. I'll be just cramming everything up into a main CPP file, and we'll just create a simulation right away. And after we are done, we can just iterate over the implementation and try to optimize it a bit. So let's begin. We are including glad for function loader as always. GLFW for window management. Some file handling stuff, IO stream and all those things, basic libraries. Nothing too fancy. We'll also maybe use GLM for math operations. Let's create macros for our resolution. I am going to use my screen resolution. Obviously, we can make it dynamic in the later stages. Let's write a frame buffer callback function. No, Vishal, they are not standard libs. C is a constant, Vishal, and we can just play around with it to get different patterns, I believe. I am I'm not familiar with Julia set as much. Like I just read it up on Wikipedia, and we are trying to simulate it and see how it goes. We'll be referring to the Wikipedia page often while coding, so that we are on track with the mathematical concepts. So the challenge here is to read the information on the Wikipedia page and try to understand and try to simulate it using our simulation. So the callback takes a window pointer and uh, a width and a height, and taking those arguments, we can those parameters, we can just give a call to GL viewport. Here we go. We can also create a method for processing input. It will take a pointer to the window, and we can use uh, the simple glfw get key method for just checking if that key is pressed. We'll call this process input method in a main render loop. For now, we'll handle just escape key for exiting a simulation. So glfw window should close. It's it returns a boolean value which we'll use to run our while loop, and if it is false, then we just exit out of our rendering loop. We'll initialize glfw, we'll set window hints. We are just specifying the OpenGL version that we are using. We are also specifying that we are using the core profile, not the legacy one, the old methods. And after that, we can create a window. Let's pass in the dimensions of our window and the title. The other two arguments could remain null. These are for getting monitor if you have a multi-monitor setup, and for full screen. So we are just going to do a windowed simulation, so that won't be an issue. We'll just check if window creation is successful. Then we make the context of a frame buffer to the current window, so that OpenGL knows that where to render. It is basically like telling OpenGL that we are using the frame buffer of our window after it is created as the default rendering frame buffer. Then we will initialize glad. So that's done. I think we should write a shader class for compiling a shader. We'll be using an unsigned integer for holding the ID of a shader object or a shader program, whatever you call it, and maybe we'll also add name for the shader. Let's write the constructor. So we are not using any kind of a geometry shader. So we'll be just creating a constructor with vertex path and fragment path. And let's create some helper method as well, which will help us to load the file and do some compiling of the shaders. We'll create a method named load file, which returns a string and takes in the path of the shader file as an argument. So this will help us loading the buffer from the shader files, and then we'll create a method called compile shader, which takes string as an argument, which is basically for the source code of our shader file, and it will take a boolean value is vertex. So we'll just use this to check if we are trying to compile a vertex shader or a fragment shader. Let's complete this method first. So we'll require a variable to store the code. If stream variable for the file, and we'll also set some exceptions. Then we'll use a try and catch block for exception handling. Let's open the file first for the specified path. Then we can create a string stream, and we can redirect the file buffer to this stream. We'll close the file, and then we can redirect the stream's content into our variable name code, like so. We are done with our try block. Let's create a catch block in case we fail to load the buffer. We can be a little bit verbose about the error, so we'll do e.what. I think that's it, and then we'll return our code. Let's come to the compile shader method. Here we'll require some variables to check whether the compilation was successful. So let's create int success. A infolog variable for storing our error message. We are using the C style string here, like character arrays, because the function that returns the error, it is actually returning in this format, so we'll be using this rather than using the std string. And we'll also need unsigned int for the shader. We'll check the condition. If it's vertex, then we'll use gl create shader. vertex shader. Otherwise, it will be a fragment shader. That's done. Now we can specify the shader source. Shader. Yeah, we need to convert this source code that we have to a const char star type. Like so. And the last argument would be null. Vishal, if I have to explain in short, shaders are like part of the graphics pipeline. Uh, they are like specialized programs that run on your GPU, and they process the, like, basically there are two shaders, vertex shader and fragment shader. So vertex shader processes your vertex data uh, in clip space, and uh, yeah, and after that it the vertices are passed through a geometry shader where you can just add or delete a few vertices. Then there are a few stages like rasterizer and all, and after that a fragment shader comes, which basically, based on certain conditions, it colors your pixels and you get a final rendered image on your screen. I hope that makes it clear. That was just a brief explanation, and I don't think that would be enough for understanding what a shader is exactly. Hi Ansh, how are you doing? After specifying the shader source, we will just compile it. Um, Triangle mesh, yeah, basically any geometry is specified with vertices. So whenever you are, maybe let's say, rendering a triangle, so these vertices are specified, and uh, these vertices are sent to the vertex shader first, where maybe you can decide to, let's say, translate those vertices. So let's say in terms of Blender, whenever you try to, translate or rotate any of your geometry using those gizmos or arrows, as you might know them, then basically in vertex shader you multiply the vertex position by certain transformation matrices to achieve those transformation. Hi Sohail, hi Ansh, I am doing good. I was just working through this simulation. It's known as Julia set. It's a mathematical concept. I was just going through the Wikipedia definition right here. So this is what it looks like, and we are trying to replicate this thing right here. So we just uh, skimmed through the basic Wikipedia definition, and like we just took a look at this formula, and basically this is what we'll be using for rendering this and creating this simulation. Oh, really? Maybe you could tell us something that this page might not specify clearly. It would be really helpful. So basically the approach that I have come up with is to use fragment shader and go pixel by pixel and check for this condition, like whether it fits in this condition or not. And otherwise, like if it fits that condition, then we'll be using a shade of color for coloring that pixel. And if it does not, we'll use a different shade for that pixel. One more method could be like we can just treat it as some kind of a geometry and use triangle primitives for rendering this, but it would be kind of overkill for that because there would be too much of vertices seeing looking at the geometry, like because it just goes on continuously, like even if you zoom into it, it is acha okay only seen. Yeah, so let's continue with the basic abstraction that we were writing. So I'll not be using the crochet engine ka uh, abstraction that I have created. We are just creating a simple basic abstraction so that we can make this thing work. Now after compiling the shader, we can do some error handling. And this is where our success variable comes into picture. Now we'll try to get the info log in case our compilation fails. We'll specify the buffer size, which is 512 bytes, and info log itself. Then we can just do a error log. I think that's okay. And we can also print this info log. Yeah, after the compilation we can return our shader, and let's write another method for creating a shader program, which will take a reference to the vertex shader object and fragment shader object. We will assign our member variable mid to the id returned by this method gl create program. So this basically in the internal OpenGL system, it returns an ID for our shader program to be used. Then after creating this shader program, so this shader program is basically, let's say, a, a thing or a, let's say, yeah, a thing that glues together different shaders to get so that we can use them while rendering our geometry. So let's say we have a vertex shader and a fragment shader. We attach those to this shader program, and when we use this shader program, then basically we are effectively we are using those two shaders, like the vertex and the fragment shader. Let's attach those. And finally we link the shader program. We will check the link status and store it into the success variable. Ansh, maybe at the end of the stream, we'll create a server on Discord and I'll share the link in the chat. Maybe if time permits. After linking the shader program, we will delete the vertex and fragment shader which are no longer needed as they are a part of the shader program, and we don't need these individual compiled shader programs. Yeah, shaders. Yeah, that should do the work. And yeah, in the constructor we can just use these helper methods for creating a shader program. So we will also create a destructor. A method to use the current shader. Then we will make a method for setting some uniform values, so we can change some parameters of the Julia set in real time using our UI. Let's make a templated function which will take the name of the uniform variable for which we are trying to set the value, and a constant reference to the value itself. We'll get the location for the uniform variable. For setting vector 2s and vector 3s and other vectors or matrices, we'll have to use the GLM value pointer. It is nothing but it basically returns a pointer to the first element of that vector. We'll use the same for a vec3. And for setting mat4, this third parameter is for transpose, so we'll specify it as false. We don't want to transpose our matrix while sending it to the uniform variable. Okay, so our shader class is done. Yeah, that's done. Now let's create a VAO and VBO for holding our vertex data and attributes. We will bind our vertex array first. Then we will bind a buffer. So like we'll have to bind a buffer after binding a vertex array, so we can specify our attributes format, like the offset for each kind of attributes in our vertex data. Yeah, sure, Ansh. You should study. See you later. Good luck with your studying. We will bind our VBO to this array buffer. And then let's specify the buffer data. We have not yet created a array for vertices, but we will do that soon. So we'll pass in the size of vertices in bytes, then the data itself, vertices, and the method. In this array, let's create a quad, and we will specify the data in NDC. So basically this vertex shader takes data in clip space, and we are directly providing it in clip space. So we won't require any transformation matrices for our quad, because then the quad would by default be rendered on the whole screen. Here we go. And after that, we will specify the attributes. Right now we just have our vertex positions. So we'll just specify one attribute. We have three coordinates for each vertex. So at location 0, we are specifying three coordinates, and then the type of data, which is float, and it is not normalized, so we'll do it as false. And then we'll have to specify the stride value, and it would be of 3 bytes, not 3 bytes exactly, 3 times the size of float, 12 bytes. And we'll require a null for the start value, and then we can unbind our vertex array. Now we will set a callback, the one which we created on top, and let's proceed with our main render loop. We will call glfw poll events for polling any key presses. We will set the clear color to black. It won't matter anyways, but we are still setting it as black. And we will be clearing our color buff a bit. We will bind our vertex array, and we will also use the current shader. We have not created a variable object for our shader, but we will soon do that. And we can give a call for drawing using our primitive as triangle. Then we can unbind our vertex array. That's a simple render loop, and later we can just clean up our resources. So we have created our basic template, a render loop, and some basic abstraction. Now what we have to do is to create basic vertex and fragment shader so that we can move forward with our actual Julia simulation. But before that, we will take a short break and I'll be right back. Mysteries of the bladder folks. I am back. I am back, and now we can continue with our implementation. Last time we just completed with the abstraction, and let's create a basic vertex and fragment shader just so that we can check if our implementation is error free. We don't need any matrices for transformation of the vertices because we are directly providing our coordinates in the clip space, and basically we don't require any transformation. We'll be directly rendering everything onto a single quad which just occupies the whole screen. And let's use GL position and set it equal to our position like so. And in the fragment shader, we can just set the out color as white for now for testing. Like so. Let's check once if we have declared everything all right. Yeah, we need to create a shader object as well. Let's create that. That's done. Let's write a CMake file. We can include fetch content. And we will do fetch content declare. I'll have to check the URL for GLFW repository. I'll just do that. github.com/glfw/glfw.git. Tag is 3.3.9. That's done. Now after fetching the content, we can just do fetch content make available. glfw, and we do find package OpenGL, which is required, and we will do add subdirectory glm. Yeah, let's let's first add these libraries, glm and glad. I'll just copy those from my downloads, like so. And for this glad, we'll have to specify the include like this. Yeah, and then we can do add library. Let's add add. We want it to be static. We'll specify the source. Target include directories. For glad, it would be public, and we will specify the path to the include folder. And after that, we can do add executable. And the executable would be named Julia, and it will take main.cpp. We can do target link libraries. We will do public. OpenGL, then glm, glfw, glad. I think that should do the job. Let's create a build directory. Let's cd into it and run cmake. Let's build. Okay, we have some issue here. Let's try to fix that. It's somewhere in the shader. Shader program here. Info log. What's wrong here? In member function, create shader program, invalid operands of types const char. Yeah, I missed one angular bracket here. Let's build it. Yeah, we can see a white quad. So this means our implementation is successful. And now what we are left to do is we need to create this Julia set logic in our fragment shader. Maybe let's integrate IMGUI as well. So I'll first have to clone that. Let's do git clone. Yeah, so let's include we will require some of these from IMGUI. I think I just cloned it into here. Yeah, we'll move it outside. We don't require that in the build. Yeah, we require imgui.h, and from the backends folder we require its implementation for GLFW and OpenGL 3. Now we have that, and maybe before our render loop we can initialize dear imgui, maybe here. We will do imgui check version. We'll create a context for imgui, and then we can get the IO. We can set the style to dark. And we will tell it that we are initializing it for OpenGL. GL should be capital here and init. And here we'll have to specify the version of OpenGL we are using. We are using 4.6 core. That means we are not using the deprecated functionalities. After that, we can create a new frame for rendering. Here we go. And after that, what we can do is imgui begin. We will write, we'll name the window as properties. imgui end, like so. And before swapping our buffers, we would like to render our window of imgui. So we'll call imgui render and imgui OpenGL3 render draw data, and we will pass imgui get draw data. We can add a simple text just to know for sure that it's working. We'll name it Julia set simulation because why not? And we'll have to make some changes to a CMake. Let's add another library. Let's name it imgui static compilation, and yeah, let's specify the source. We'll need that. We will also need imgui draw, tables, widgets. Yeah, I think that's it from here, and from backends we will need some files. We'll require one for glfw. I don't see it. Yeah, it's right here. And one for OpenGL3, like so. We'll do target include directories for imgui. It would be public. And let's link it with our executable. Let's build it. We have a typo here. We'll just fix that. Let's build again and let's run. Yeah, see, we have a window here from imgui, so that we can use it later for adjusting our properties for the Julia set. Now coming to the meat of this simulation, let's take as uniform the resolution, uniform vec2 let's name it URes. That would be the resolution of our screen or our window. And let's do vec2 suv is equal to, we'll get the fragment coordinates using the inbuilt variable frag chord. We will require xy and we will divide it by u res. So now we are dealing in normalized device coordinates, and we will also require aspect ratio ures dot x by ures dot y. Now we have these. Let's go to the whiteboard and we can just try to map things out so that we know for sure what we are trying to do. I hope it's visible. Yeah, I'm using Krita for just drawing simple things like planning our strategy. So for our coordinates, like the pipeline goes like this. So let's say we have some vertices here. Let's name it V1, V2 and V3. These go to the vertex shader. Right now what we are doing is we are providing these in clip space. So basically vertex shader, there is one variable, internal variable named GL position. I am calling it as GL underscore pos for short, and it takes in the coordinates in clip space. So we are directly providing in that, and after that there is geometry shader. So we are not utilizing any functionality of geometry shader, like we are not modifying these vertices in geometry shader. And after that a few more steps and then we have the rasterizer. So basically in between these steps there is a step called clipping. So basically there is this cube of uh, like dimension ranging from minus w to w. So basically these vertex positions are a vec4. So we have x, y, z and w, like so. And these range from the view cube ranges from minus w to w, and basically anything that just comes out of this range is basically clipped away. So basically this won't be visible, and instead what we do is replace this vertex with these two clipped vertices, which are basically to confine this geometry into this view volume. And after that go to the we do the viewport transformation, which basically maps the uh, normalized device coordinates to the screen coordinates. And basically so we have the before that we actually do perspective divide. So basically this cube ranges from minus w to w. What I mean by this cube is basically each side of it ranges from minus w to w, and after that we do perspective division. So basically all these coordinates in vec4 x y z are divided by w. So basically we get a range of minus 1 to 1, and these are our normalized device coordinates. So basically, let's say we have a screen. So the normalized device coordinates, we have the origin at the center, and this is minus 1 comma 1 minus 1, and this is 1 comma 1. So this is basically mapped to the screen. So this would be actually a square, and we map it to the screen like so. Let's say this is a screen. So basically this is mapped here, this is mapped here, this is mapped here, and this is mapped here. So basically this is projected onto the bigger screen. So this is what we call as the viewport transformation, and after that we have a rasterizer. So this rasterizer basically generates fragments for the geometry. So let's say we have a triangle, so it will try to calculate these fragments, like how many pixels and what pixels are fitting into this geometry, and then it will just run the fragment shader for each of this fragment, and thus it gets a color. So fragment shader, and we have our rendered image. Forgive the poor handwriting, I'm using my mouse for writing stuff, so it's not that good, but I think this makes the point clear. This is basically the graphics pipeline overview. There are some of the steps which I have skipped, but yeah, this is generally what you are dealing with when we talk about graphics pipeline. So right now we specify everything into these normalized device coordinates. So this is basically a square. So the problem we have to fix is the aspect ratio. We'll have to use that, because like this square would be mapped to a screen which is 1920 by 1013. So basically the coordinates in the x would be stretched to fit this screen right here. So what we'll have to do is we'll have to so aspect ratio is width by height. So we'll have to multiply the x coordinate of this into 1 upon the aspect ratio. So technically what we are doing is when we multiply it by 1 upon the aspect ratio, it's as good as multiplying it by height upon the width. So basically dividing it by width, it normalizes it into minus 1 to 1, or rather 0 to 1, and then we multiply it with h. So it's basically effectively transforming this space into h cross h, and so the image won't get stretched. So let's do that. uv is equal to vec2 uv dot x times We'll divide it by aspect ratio and uv dot y. Yeah, we have these coordinates. I did not change weight. Yeah. So I have these coordinates now, and the the x coordinate is divided by the aspect ratio, and the scaling thing is fixed. Now what we have to do is we have to somehow figure out if this Julia set thing fits our current pixel or fragment. So let's take as uniform a value from the user for, let's say, the number of iterations that we have to do and the constant value. So the formula for Julia set was z square plus some constant. So we'll take that as uniforms. UC is basically that constant, and we will also require max iteration, so we will use an integer for that, like so. And let's use int right here. We'll create a for loop. It's because we have to iterate over different values for calculating each point. So it would be less than max iterations. And basically we have to calculate z square. So what we will do is float x equals z dot x into z dot x minus z dot y into z dot y plus uc dot x. So this is basically I'm squaring z in complex plane. So yeah, there is this iota factor as well coming into picture. Like so. And we will set z equal to x comma y, and we will check if we will need some kind of condition, right? So let's say uh, if we diverge, then we'll have to check the condition to break out of the loop. So let's try to find out the value for where Julia set actually diverges. Each point of the Julia set is a point of accumulation for each of the Fatu domains. I don't know how to spell that. Therefore, if there are more than two Fatu domains, each point of the Julia set must have points of more than two different open sets infinitely close, and this means that the Julia set cannot be a simple curve. This phenomena happens, for instance, when f of z is the Newton iteration for solving the equation. Okay. A very popular complex dynamic system is given by the family of complex quadratic polynomials, a special case of rational maps. Such quadratic polynomials can be expressed as this, where C is complex parameter, fix sum r greater than 0 large enough that r square minus r is greater than equal to C. Okay, then mod C should be less than equal to 2 so that we may simply let r equal to 2. Then the filled Julia set for this system is subset of the complex plane given by this. Okay. So what I can make out of this is that we have to set a limit of 2 so that it does not diverge. So let's use that. We will use a dot product and check if it's greater than 4. If yes, then we will break, and let's create a variable named t. It will be, let's typecast iterations, and we can create a simple gradient for our fragment color. Yeah, I think this is it, and we can just pass these from our main program. We will typecast them into float. We will also require UC. Let's try to get the value from these examples itself. For this, they are using minus 0.5125 and 0.5213. Let's use that. And 0.5213. Now we'll have to set the maximum iterations. Let's set it to 300, just an arbitrary number. We can tweak that later. Let's build it. Okay, we don't see anything here. That means something is wrong. Let's check that. Okay. Oh, Z is undeclared. Yeah, we made an error. let's do vec2 z is equal to this. Yeah. Finally, we have got some Julia set pattern here, but it appears to be weirdly scaled, I think. So we'll have to do something about it. It seems stretched. Let's try to. I think it should be multiplication. Yeah, it's better. We actually needed to multiply it by the aspect ratio. Yeah, my bad. So right now we have this. This is a Julia set, but I think there is some offset here, and we have to fix that so that it works all right. So right now we basically the screen coordinates are normalized, but they range from 0 to 1, and this thing actually revolves about the center. So most of the things are clipped here. We need to center this thing around a screen center, and for that we will have to do some kind of scaling. So right now we have this quad, let's say it is ranging from 0 to 1, and we need to change it to, let's say, -2 comma 2. So what we can do is we will first subtract zero point 0.5 from this, so it will become minus -0.5 comma 0.5, and we can multiply it by 4. So this effectively becomes -2 comma 2. So what we'll do is mm, before doing this we can do uv is equal to vec2 uv dot x minus -0.5 into 4. I think this should make it look better already. I'll just um, set up this so that it displays the output. I think last time when I ran my simulation it was not visible, so let me fix that. Here we go. So this is our Julia set simulation. It is looking quite good already, but what we need is a bit more flexibility and controls in our UI so that we can mess around with this. This is already looking really good. So let's get working. Right now we have scaled it like so, and maybe let's add a few sliders for that. I'll create vec2 for UC. I'll copy those previous value. It was minus 0.5125 and 0.5213. Let's set it to 300. And in this, let's try to get the frame rate as well. Like so, and here we will pass the variables that we created above, UC and maxiter. Yeah, and we need to create sliders for changing these values. So I think it was, we will check from the IMGUI examples. What was it exactly? Let's try to search for slider. Yeah, slider float. We need a float slider. It takes a string, the value itself, and the range. Okay, and the format. Okay, so let's add that. Slider float, and we will do uc.x, the value itself, we will do uc.x here, and let's give a range from 0 to 1. That should do the magic. We will add the same slider for this, the Y, and let's add a slider for iterations. Now we'll have to search for um, a field we need a text box for input. Or maybe we can use a slider int. Yeah, that would be better. Max iterations. 0, and we can take it up to 1000. Let's try to compile it. I think we'll require the address of this. Frame rate. Okay. I think the R was capital in this. Let's hmm. Yeah, we need to. It must be has no member frame rate. Did you mean frame rate? Hmm. I think it was right. Yeah, we don't require those brackets there. Yeah, so right now we are getting frame rate as 60, around 60. Yeah, and we can change these values right here. We are seeing some interesting patterns here, and we can really change the colors based on the iterations we are using. Wow, this one looks amazing. Max iterations at 11, and yeah, this gives me an idea that we can use it for procedural terrain generation, like for creating map dynamically. That would work out great. This is the output that we have. Sorry, I forgot to share this output screen. So yeah, we can change these parameters like so. This looks really amazing. We are seeing some interesting patterns here. We can change this. And it doesn't seem to affect the frame rate much, like we are almost getting a constant 60 fps around, roughly around that. We can make it vary with time as well. That would be great, like it would look like an animation, but we'll have to find a range in which it is having it is retaining its shape, otherwise there won't be any sense in doing that. Increasing the iterations is just doing something to the color. It is looking kind of grainy, and if I decrease the number of iterations, then it gets this sort of pattern. This is also great. Like, I was thinking this will help me out in terrain generation in my game engine. Like, I can, map out these colors. Let's say this color for height, and like this looks like a hill kind of hilltop or something, which I don't know. This is the top, and slowly there is something like in topology. There is something, you represent these mountains and all from this top view, and you keep on drawing circles around. I don't remember what it is called, but yeah, it can be used for terrain generation. This already looks great. Now let's try to add more functionality to our implementation. Let's try to add an ability to zoom in and out so that we can, try to look into this much clearer. Let's create a variable. I think we'll have to make it global. Let's set it to 1 for now, and we'll have to create a callback for that. Um, we'll call it scroll callback. And what we will do is, if our y offset is greater than 0, that means it's positive and we are trying to zoom in that case we should be multiplying zoom by, let's say, 1.1. Otherwise we will divide zoom by 1.1. And we will set this callback here. LFW set callback, like so. Now this will change the value of zoom based on our scrolling. Let's name it U zoom. And we can set the value right here. Now we will add that uniform right here. And what we'll have to do is z equals z by zoom. We will divide by zoom. So let's say we have our coordinates ranging from 0 to 1, and let's say our zoom is 2. So when we divide by 2, so basically our range is now shortened from 0 comma 1 to 0 comma 0 0.5. So basically this is zooming in, and let's compile it. Okay, we have an error. Okay, we need to change the variable name in the callback as well. It should be uzoom. Let's build it and let's run this. Here it is. Now we can zoom into this, and you can see we are able to get deep pretty much, and we can just change the number of iterations and all to get interesting patterns out of this. Maybe let's do it this way, change this a little bit, and iterations we can reduce it a bit. Yeah, let's try to zoom in. That's great. Like we are getting almost that infinite zoom effect, but right now, like after a certain point, we can see a bit of pixelated things, pixelated artifacts, I would say, and those don't look much good. I think that's because the single floating point precision that we are using, and maybe we'll switch to double floating point precision, but that would be a bit compute heavy. And right now we are getting around, it's actually varying, the frame rate is varying, but still if we reduce the number of iterations, we are actually getting a rise in our frame rate. That's obvious. Interesting patterns here. This implementation could use some optimization. Frame rates are not so good. Like for less iterations it's fine, but when we increase the number of iterations, then the frame rates drop a bit. To see that better, the drop in frame rate, the numbers are not helping much. We can maybe create a plot for that, which will help us visualize what's exactly happening. So let's do that. So for creating a plot, we will have to create an array for storing the points in the plot and the index for it. So what I am going to do is, right here I am going to do static float fps history, and let's store 256 points in it, and we will initialize everything with 0, and static int history index, we will set it to 0, and fps history at history index should be io.framerate, and history index is equal to history index plus 1, and we will do mod 256. So we are basically wrapping around like so, and we need something to plot. Let's see. IMGUI plot lines, so we will use that. Just below the frame rate counter. Let's try to build it. If you can see, we have a tiny FPS plot running here, which will show us any drop in our frame rates. So right now it's showing a peak. Guys, if you're watching and have not subscribed to the channel, please consider doing so. That's working alright, but maybe we can improve the plot a little bit. We can give the history index and we will call it FPS. We will clamp it between 0 to 200 and we will increase the size. Let's compile it. Here we go. Now we have a better profiling right here, and we can easily detect any drop in frame rates. Yeah, as we zoom in, we can see the drop in our frame rates. We'll have to fix that as well. And also I think we should add some panning as well, so like clicking and dragging should enable us to move around. Most of our setup is looking all right. We just need to add panning, and for that I think I'll use a variable, let's say a boolean is dragging. I'll set it to false, and maybe we'll require a vec2 for center. Like so. So guys, if you're watching and have not subscribed, please consider subscribing to the channel for more such live streams. and we will create a callback for this. We'll call it a mouse button callback. So what this will do is, if the button we press equals glfw mouse button left, and if action is glfw press, so if we are holding down our left mouse button, what we will do is we'll set is dragging is equal to true, and we will do a uh, poll for the cursor position. glfw get cursor position. It should be pause, I think, cursor pause, and a pointer to the window and reference to x and y. This will basically, let's create them as global x double y. I'll set them to 0 at first. Yeah, and let's say if action is released, so when we release our left mouse button, then we set is dragging to false, and we will also require one more callback, void we will call it the cursor callback. And what we need to do is, if we are dragging, like we are holding down our left mouse button and we are dragging, then we will calculate the difference. We'll also have to create variable for tracking the last position. After doing that, what we do is we set last x equal to x and last y equal to y, and we create a scale factor. So the scale factor will also compensate for the scale of our current zoom. So it should be 2 divided by zoom times the height. Like so, and we have use center. We will set its x value. We'll actually subtract dx from it, and we will multiply it with scale and the aspect ratio. We will typecast it to float, and use center.y should plus equals dy times the scale. There we go, and that should do the magic. um, yeah, we will set the uniform from our shader. Let's add a uniform here. And we will add this to our Z. Let's build it. The panning doesn't seem to work right now. Let's see what's the issue. We are not setting the callbacks here, that's why it's not working. So let's set those. We'll have to set a mouse button callback and a cursor pause callback. Let's build it and let's run. It still doesn't seem to work. Let's see what's wrong again. I think the callbacks values are swapped. It should be button first and then the action. Let's build it again. Let's run it. It seems to work, but not that well. So right now if I show you what's happening, if I zoom in, it it is just jumping to that position. It's not panning smoothly, so there must be something that needs to be fixed. The panning is working, but there is some issue that is preventing it from working smoothly. So let's fix that. We are calculating dx by subtracting the x position minus the last x. Oh, basically we should be subtracting x position, the value that we get from the callback, not the value that we get using the cursor pause method. So we will use x pause here, y pause here. Let's build it. Let's run. Now let's see. It seems to work, but it is really quick. Let's restart it. It is really fast. We need to scale down the panning a bit. Yeah, we need to change this as well. Let's build it again and let's try it out. Yeah, now the panning works smoothly. But it snaps to that click position. That needs to be fixed as well, so let's fix that. It has to do something with the starting position. Okay, so I'm not actually getting the cursor pause callback in the last X and last Y. So I'll use those. And I think this should be it, like this should work right now. Yeah, it works like a charm. And you can really see the infinite zoom in action. This panning thing actually messes with the UI that I'm using. I'll have to fix that. Right now what we are doing is setting the callback directly, but it should allow us to switch between the UI mode and the panning mode. For that I'll have to do something. Let's first push it to the repository. We pushed our changes to the repository. Let's try to search if there is a method to disable a callback. This is actually how we set the cursor position callback, but let's find out if there is a method to reverse that. Or instead, we will leave that callback as it is. I don't think there must be any method for that. We will leave that as is, and inside of that, where we process the input, we will check if a certain mode is enabled. So we will create a bool is panning, or maybe we can use the is dragging variable itself. Let's see. I think we require a separate variable. And we will use that in our callback. and we can use this process input method for checking if we are panning. Let's say U. Let's build it. Yeah, I cannot pan right now, and once I hold U, I should be able to. Nope. There seems to be some error again. Yeah, we are not calling the process input in our render loop. That's why it's not getting updated. Let's build it again. Let's run it. Yeah, now holding U allows me to pan. And now I should be able to. Nope. It won't allow me to use the IMGUI menu. So I think one thing I can do is to pan, I can use the right mouse button. So right now right click allows me to pan, and I still can't use the IMGUI menu. I think it has to do something with the callback. Let's try disabling the callback. No, still can't use it. Maybe it's the cursor position callback. Yeah, now I can change it. I think the cursor position callback is messing up the controls with IMGUI. So what I'll do is, maybe we can fix this later. Right now we have a simple working implementation in place. Here we go. I think we will leave it at this, and I'll create a Discord server and I'll just share a link in the chat. Or maybe we can do it next stream because I don't think many people are watching right now. So maybe during our next stream, I'll share the Discord server link. And what I think is the current implementation is good, like it is working. We need to fix that UI thing, like when I try to use the panning ability, then it does not allow me to use this IMGUI UI. It is, I think, somehow conflicting with that. So we'll have to fix that. And also, I was thinking, right now we are using fragment shaders for rendering this. I was thinking if uh, let's say we can, maybe I can write a parallelized kernel in CUDA and use that for computing the value for the Julia set, and maybe I can also try implementing it on the CPU as well, um, not on the GPU. So we can then benchmark all of these three, and maybe we can use the CPU one as a baseline and the fragment shader as a baseline, and the CUDA implementation, uh, then we can try to optimize it further. So that will be our plan for the next stream. This stream was like completely unplanned, and I successfully achieved like the working of the Julia set, but it is not that complete and impressive. We can add more features to it later. So I think this is it for today's stream. See you guys later. Thanks for watching. Bye.